Borges wrote, "It may be that universal history is the history of a handful of metaphors." And the same might be said of mathematics. So to illustrate this point, let me begin by asking, where do we find mathematics? So one place we find mathematics is in the structure of the physical universe around us, where its mathematical laws reign over the interaction of elementary particles, and they reign over the interaction of galaxies and stars. But we also find mathematics at the mesoscale, the very complex intermediate scale where we have life and DNA and universities and lectures and PowerPoint. And there, mathematics is a cultural phenomenon. It's part of human culture, and it's mediated by language, which allows it to develop over thousands of years. And we usually don't reflect on the miracle of the coexistence of these two types of mathematics. So let me illustrate it with an analogy. So imagine a vast plane filled with particles evolving according to some simple law, Conway's game of life. Is it possible that after eons and eons, these particles start to form some sort of self-replicating objects, and that when viewed from an enormous distance, these self-replicating objects are writing out, say in Gothic German script, the rules for the game of life? Well, that's the world we live in, where physical laws have given rise to physicists who discuss physical laws. So now classically there's another realm where some philosophers believe mathematics exists. It's a realm of ideals. So for example, the Platonic solids are these ideal shapes, and the four types of atom that make up our world are just low resolution, imperfect replicas of these ideal shapes. Moreover, these imperfect atoms, according to Lucretius, have a built-in random element. They swerve at times. Or as they say in quantum mechanics, God plays dice with the universe. So maybe it would be interesting to consider a game with a random element, like the game of backgammon. Well, actually, backgammon can go on for an infinite time. So let's start with a simpler game with a clear winner and loser, the game of hex. In the game of hex, two players try to build a bridge. Blue tries to join the blue sides of the board. Red tries to join the red side of the board. Oh, look, young Nash just beat old Nash. So Nash proved that the first player has a winning strategy for hex, but no one knows what the winning strategy is. It's very hard to formulate it succinctly. Here's another game, random hex. Color the cells black and white at random with equal probability. It's not that much fun of a game, but it raises an interesting question, which is, what are the chances that black wins? Now, this game goes by another name. It's called critical percolation. And the reason it's called critical percolation is because when black wins, it may mean that hot water makes it through the coffee grounds, or it may mean that sea brine penetrates the Arctic ice cap, causing it to collapse, sea levels to rise, and coastal cities to disappear. Now, there's an important conjecture about percolation, which is that if we fix the table and make the squares very small, that as we go to the continuum limit, then its behavior is conformally invariant. For example, the chances that black wins should only depend on the conformal geometry of the playing table. And I'd like to explain the proof. So let me first remind you that the Riemann mapping theorem says any playing board in the world can be mapped conformally to a rectangular playing table, sending corners to corners. This map will distort distances, but it will preserve angles. Now also, it's not so surprising that conformal maps might enter into the theory of percolation, since other processes, such as electricity and fluid flow, also have a certain amount of conformal invariance to them. And in fact, biological processes, such as growth and evolution, also seem to know about conformal mappings. It seems that different species of fish or horses or primates have shapes that are related by conformal transformations. Well, getting back to random hex, if it is conformally invariant, we might as well play it in a round table. And then the table will be completely determined by the cross ratio, x, of its four corners. And Cardy, based on physical reasoning, came up with a guess for the probability that black wins in terms of x. And here's the formula. It's a little complicated looking. It turns out if we play in a unit triangle instead of a unit disk, well, then there's only one parameter, which is the location z of the fourth corner, and that formula changes to this. The probability black wins is given by the height of z, this point here. And notice that that height, that probability is also the probability that the black squares block z from getting to the bottom edge of the table. Now, Smirnov made a beautiful innovation here. He said, look, we can also ask for points inside the table, whether or not they're blocked from reaching the bottom edge. And the guess is, again, that the probability is just given by the height. Now we have a function defined inside the whole triangle. In fact, we have three functions defined inside the whole triangle, because we can ask if z is blocked from this edge, or this edge. And it turns out those three functions satisfy a triangular version of the Cauchy-Riemann equations, where I is replaced by a cube root of unity. So there's an analytic function. It turns out to be z, and that proves Cardy's formula and conformal invariance. Well, I don't want to leave you with the impression that this theory is settled, because not even no one understands percolation on a checkerboard as opposed to on a hexagonal board. But when they do, they will have simply added one more mathematical elaboration to the fundamental motif of a game in the plane. So indeed, it may be the case that universal history is the history of different intonations given to a handful of metaphors. Thank you.